check on YouTube. Since it's informal, maybe we don't have to worry about that.
Yeah.
Go. Sure. Suggest him to make you guys as co-hosts.
Yeah, it's better.
Yeah, if he drops,
I guess we can start now.
I think you can start, now
Yeah.
very incrementally and get some time.
Yeah, sure. Yeah, we'll hope you have performed at least one experiment in last 1 hour, and you got some experience over it. So now we'll go for the other two experiments, and maybe if time permits, we can discuss your problems, or maybe we can discuss over the next two new experiments. So is that fine? We'll take first two experiment, and then we can discuss the problems or the difficulties if the people have faced during their experiment. Is that fine with everyone? Desh?
yes, please.
Yeah, Ashish, can you start with the next two experiments?
Yeah.
So the next two experiments that we are going to see are one is related to a corner reflector and the other is an experiment in interferometry. So yeah, so this is a simple corner reflector antenna. So a corner reflector is formed by two reflective surfaces, conductive surfaces, and you can see the top view here. This is the front view, and the red line that you see is actually the antenna which is radiating, but because of the reflector, the radiation pattern of this antenna changes. Of course, you will get more radiation towards this direction, and less direction, less radiation in other direction. So, in this experiment, what you are going to do is pair this kind of a corner reflector with some aluminum foil or some metallic plate which can be stuck onto some cardboard plate or even a notebook. And you can place your mobile phone in front of this corner and see the radiation difference in radiation with the corner and without the corner. And you get more radiation. So this is also sort of a continuation of one previous experiment where we had one single plate behind the mobile phone. Here now you have two plates, and this is one variation of that experiment. And you can see what effect that creates on the radiation. You can check in which direction you get the maximum radiation, and later on you can actually uh, modify the corner and put a third plate uh, below below these two plates, and this will form a three-sided corner. And as you can see in this image, there is a mobile phone kept here at a particular distance. You will have to experiment with this distance. Three corners. That depends on where the antenna is located in your device. So you can move around, move this mobile phone around, and check for where you get the best your experience. And then, of course, this ground, you can keep it on an elevated platform like a chair or table. And in this case, you will also have to find out in which direction you get the maximum radiation.
Well above. It shouldn't be on the ground.
Right, right.
Yeah. It might be useful to clarify that.
Yes, yes. So, yeah, I mentioned that. So, it is advisable to keep this setup on a chair so that the ground does not affect your measurements. And yeah, also, uh, all the instructions that we had for previous experiments, like uh, keeping your connecting to a hotspot, creating a hotspot on your mobile phone. So most of the people said last time that when you create a hotspot and you are not, or you if you put your mobile phone in flight mode, you are not able to create a hotspot. So you can either disconnect from your data. So the idea is that you should not be receiving packets from the internet because that creates problem with the measurements. Or some people suggested that you can either switch off your SIM card in the settings, or you can just remove the SIM card. And then create a hotspot and see the do the experiments. So this is the first experiment. The second experiment has to do with the okay, but let's see if anybody has any questions related to the first experiment.
I have a question.
Yeah.
Do you have any, you want to say anything about the angle in the corner reflector?
So they can start with a 90-degree angle, and they can also vary the angle and see how that affects the radiation pattern. But looking at the size of the mobile phone, they may not have too much freedom with the angle.
Yeah, one comment I have, which is while we are on this topic, that with the reflectors around and the reflections uh, combining with the direct path, you will find that the directivity is changed significantly, and one way of analyzing it in your mind of the effect is to imagine a reflection of the radiator uh, about the reflector. So imagine that you had a single reflector behind. You can imagine another radiator which is placed similar distance behind the reflecting surface, and a combination of the two is what is going to lead to the, the final pattern, directivity, increasing power, and everything else that goes with it. So similarly here, you might want to imagine the reflections of these. So in the corner reflector, you would have three images, right? Much like if you had a mirror, the kind of images you would see. And so this is no different. These are actually mirrors at radio wavelengths. And so you should see a combined effect of those. Only thing in doing so, so you would take those as radiators in phase with this. In addition, after accounting for the extra difference of pi due to the reflection, and then you can combine the effect of the four radiators, okay, and what that would give you in terms of directivity and so on. So it can be formally analyzed, even analytically, using that framework. Now, as a corollary, you will find you will have enhancement of the emission in the corner reflector in a plane sort of halfway between the two plates, symmetrically placed plates. So at 45 degrees from the plates, and that's where the emission will be enhanced, which will contain the common line between the two surfaces. Here you can imagine that with the three reflectors, your boosting might take place along an axis which is inclined with respect to all the three surfaces equally. And while putting it on the location higher up, unless you orient your reflector properly, you might find that the peak is actually occurring in a direction that is not accessible to you unless you are very tall. So you can adjust your orientation of these corner reflectors accordingly. I might also add that the first two versions of the one that you heard before in the previous session of reflector at the back is a common usage in antennas that we use, particularly the ones that are looking up. We put the reflector below. An example of a corner reflector is readily found in UT telescope, where the line feed, set of dipoles along the line, are covered on the top with a corner reflector. This is to enhance its response towards the dish surface, reflector surface, rather than looking at the sky, and also to confine the directionality to within the reflecting surface. So, which means that you, after putting this corner reflector, you should go around in angle at the same, keeping the distance same, and measure the power, and you might land up measuring the response, directionality response of this arrangement in the process, and you might want to plot that as a function of angle, at least roughly, and get a measure of how much that is and how does that vary with respect to the angle of. So this is exactly like mirrors, and keeping something in front of it with mirrors with some angle, and you can actually count the number of images it will make, and so on and so forth. You can see that the enhancement you get is as if it's a result of combined effect of all these images along with the original piece. You have to take care of the phase shifts and phase differences, not just due to the locations, owing to the locations of the images, but also due to additional pi phase shift that they would have because of the reflection. So that's all I have to say. Thank you.
So can I ask a question?
Yeah.
So like, how does this compare with our, the plane back reflector that we had in the last experiment? Like, seems like for like an angle of 180 degree, basically that plane, plane reflector is just some special case of this corner reflector. So is there a relation between these two, or?
Yes, there is, and exactly as you said, the plane reflector is a special case of this, right? So you will find, in that case, you will find only one image, right? Right. So one image and the original. Now it's as if having two radiators, okay, with some phase relationship, radiating in all directions, and the combined effect of it will enhance in certain direction and will weaken the signal in some other directions.
So then also, like, I was thinking about like interpretation of these devices. So basically these are for amplifying our signal from this receiver. Oh, sorry, the radiator, this transmitter that we have.
Well, it's amplifying at the cost of reducing in some other directions. The total power radiated by the device is same. It's just directed in different directions, okay, preferentially, and it has to come at the expense of reduction of power in some other directions.
So isn't this kind of like a reverse radio dish? So for example, I think of this as like, if I keep this radiator at like the foci of a parabola, and then this the dish that I have is basically this.
That's exactly what we have at UT. Yes.
Right. So that's basically an inverted radio dish, right? For like maximizing this.
Depending on which way you use the enhanced response, whether you use it to collect radiation that is from a primary reflector, shaped reflector, or you let it look up where the response is directly looking at the sky. And in any case, there is a certain reciprocity here. Okay, what you see in radiation is same as the characteristics will be similar to what you would have in the reception. If you were to use this as a receiving antenna also, it will have the same relevant characteristics.
Yeah. Yeah, that makes sense. Thank you.
Yeah, and as you mentioned, uh, this is sort of a modification of the previous experiment. So you have to actually determine the difference that you see when you have just a plain reflector, and then you put a corner like this, and then you add a third reflector, and then you have to see what amount of boosting or gain in signal you get. So that is one of the goals of the experiment. And also, as Desh mentioned, if you can move uh, around this setup and measure the received power and the angle, then you can actually plot this response of this antenna. So how it radiates and in which direction you get more radiation, in which direction you get less radiation. So that basically forms the response of the antenna.
Okay, thank you. Would reflector be like quite better compared to this because it will be at like all the end of the reflector will be at constant distance from the antenna, like consider lambda by 4 lambda by 8 or somewhat similar. So won't it be better to use those reflectors? Sorry, your initial part of your question was not very audible. You repeat first part of your question? Okay, I was talking like as if we use parabolic kind of reflector, then the distance between reflector and antenna will be constant, irrespective of whichever point you take as a reference. So won't it be better to use those kind of reflectors? No, I think maybe you're confusing between spherical reflector, right? That's where the distance will be constant. Yeah, but, yeah. But I know what you're referring to. You're referring to the radiator being put at the focus of a parabolic reflector, right? Yes. Yeah. In which case, yes, you will find that you eliminate the reflector, okay, with this radiation in such a way that in the plane containing the rim of the parabolic reflector, okay, will be having equal phase. It would have traveled the same distance to the plane containing the rim, okay, from the focus. And that's the property of parabola. Yes, so it will be kind of better than using this kind of reflectors, right? Yeah, these are easily made. Making a good parabolic reflector, unless you have, readily have access to a dish, okay, which you might have. We just wanted to keep it simple so that people can experiment with things that are readily available with them. But you are absolutely right. This is what one uses. One doesn't use this kind of a reflector to uh, as a as an antenna generally. If one has so much surface available, one might even make it a paraboloid and put the radiator at the focus or receptor at the focus, and that is the traditional paraboloid dish configuration, which people routinely use. Except you will find that that will also make now the radiator size will be the reflector size, and you will have to take into account the near field, far field considerations explicitly, right? Even here you might need to make, but this will still be a compact configuration, okay, of radiators and images of it.
Yeah, so I hope everyone has some access to some aluminum foil, uh, so that they can prepare these kind of sheets with either your notebooks or some cardboard sheets. So this is just aluminum foil stuck onto a cardboard sheet. and we prepared a corner. And you can use some, here it is a thermocol on which this mobile phone is kept. So you can cut the thermocol and change the distance between the reflectors and the mobile phone.
If I were to do it, I would be concerned about lack of knowledge of where exactly the antenna of this mobile phone is
Yes.
in terms of radiator. And I'm sure some of you also have this concern. And one way of finding that out is to go back to the second experiment that was described this before this session, where you had the lambda by 4 distance to be the optimum, right? Now you can mark that spot and bring different parts of the mobile phone at that location, okay? And the one where you get maximum signal is the one which will sort of help you locate the area where the antenna, radiating antenna might be situated in within that plane of your phone.
Yeah, so you can try different orientations of the mobile phone to figure out, in case you don't know the location of the antenna in the mobile phone, you can try different orientations of the mobile phone and see in which orientation and at what distance you get the maximum power, and that should correspond to the location of the antenna.
So it will be nice that each one of you figure out where in your mobile set the antenna is located without somebody telling you, the manufacturer. See if you can figure that out.
One more thing we need to take an account while performing this experiment. So whenever you're connecting to a plain like cardboard and you stick aluminum foil on it, so make sure that there should not be much gap. Okay, so at the connection where they both corner are connected. So maybe for example here you can maybe Ashish can show. So yeah, so you can see it's completely filled and it's it's covered with aluminum foil properly here. So make sure
Yes, at
that
the
those are
corner,
not
yeah. That's what you're saying, right?
yeah this one.
Yeah, so the corner should be connected.
Well connected, and it will be good if they are covered with aluminum foil.
Well, they should be electrically connected.
Yes.
Because if there were to be gaps, don't be surprised that the gap with metal around it will also act as a radiator in its own right. These are called slot antennas.
So aluminum is necessary, or plastic sheet would work with this?
Pardon?
If you're using plastic,
Would plastic sheet?
plastic sheet won't work. You have to cover with aluminum foil. You need a metal.
It has to be a mirror at radio frequencies, okay, and a reasonably smooth mirror, and the smoothness, as long as it's smoother than lambda by 20, okay, it's okay. Small wrinkles here and there will not matter too much.
Okay, so but metal isn't necessary, right?
Pardon?
Like we need only reflection. Like
yeah, we need a good
we need only reflections.
Okay? Plastic may not reflect very well.
Okay,
It
so
might reflect only
it's
partly. Partly it will be absorbed.
okay.
Sir, copper clad is fine, right?
Copper what?
Copper plate is also, it will work.
Yeah, copper plate is fine. Even steel plate is fine. Okay.
Any metal which has
Any
like good
metallic
conductor.
Yeah,
plates.
and the thinness, why the foil works, why you don't require a thick plate, is the amount of metal that is in that is participating in this process of reflection is only what is called the skin depth thick. Okay, a few times the skin depth, and you can actually look up things about skin depth, and of course they are frequency dependent and all that. So you can figure out at the frequencies of relevance what should be the minimum thickness required for the metal, whatever surface, whatever covering that you put like a foil.
Sir, if we use the aluminum foil and we don't use the cardboard covering behind it.
That's okay. Cardboard is just for support, just for some.
Alright. So wouldn't it was like
foil in place? It's good enough.
no, sir. I meant that can there be an issue of transmission instead of like reflection? That is why we put a cardboard behind it.
No, cardboard is not playing any important role in interaction with the electromagnetic wave.
All right, sir.
It's just acting as some dielectric material. Okay, might have some amount of absorption. That's about it.
So there can be transmission through the aluminum foil as well.
No, it won't be. There won't be if it's thicker than few times the skin depth.
I think the skin depth for aluminium is roughly 1 micron meter. So,
Right.
Yeah, so I don't think that's going to be much of a problem.
Correct. And I think the foils are much thicker than that.
Yeah.
Yeah, so shall we move to the next experiment?
The 3-corner reflector, if you find it too difficult to make or have difficulties, you might even use a cavity-like thing, which is one burtan, one pot from your kitchen, if you can steal. Except you need to keep this roughly at the symmetric point.
And so, what is the role here the thermocol bases are playing over here? They're simply used to hold the mobile phone, or what is their purpose actually?
Yeah, it's just to raise the phone. It could have been something else. It could have been even a cloth.
Okay, so fine. Okay. So
Can I add something here while we are on this topic? Nobody has raised this question, but
yeah,
people might face this issue or might have concerns quite independently, is something about the polarization. The radiator might have some specific polarization, or your receptor might have some specific polarization. Normally, they are not expected to have strong polarized characteristics in terms of picking particular linear polarization or something. They would rather be more circular polarizations, so that so the issue is like having two polarites, right? And how the relative orientation of their optical axis will change the way you get the reception or filtering from one. How does it what fraction of it is received by the other? So be mindful about the possibility that some devices might have some more linear polarization, okay, than being circular. they are certainly 100% polarized. That much can be told. So you might want to, the orientation aspect that Ashish was mentioning would also be changing that aspect about the way
Right. Yes.
polarization, plane of polarization is oriented, if at all it has any linear. Yeah, sorry for that. Extension.
Hello, sir.
Yes.
Will the when calculating the maxima and minima of this, the traditional interference and diffraction formulas will they come into play when calculating the maxima and minima for this?
You can look at it that way as well, right?
Yes, sir.
After all, in the simplest possible case, right?
Yes,
Why
sir.
the reflection from the mirror from all parts of the surface. For a very preliminary investigation, you can take only specific rays, right?
Yes.
And work out the primary expectation, okay, from these.
Yes.
So for that, as I suggested, you might think of with this mirror arrangement, the images, the locations of the images, and imagine radiators there. While doing so, of course, you need to be very sure of having accounted for the extra phase difference
Phase difference. Yes.
due to reflection, in addition to the extra path lengths that things would travel.
Yes. Yes. Okay. Thank you, sir.
Yeah. Okay. So the next experiment is the sea surface interferometer. Here you have a transmitter and a receiver. Uh, Here, suppose your laptop is kept at some height, and you have your mobile phone which is transmitting. So you keep some fixed distance between your laptop and the mobile phone. So there are some known quantities in this setup. For example, you know the height at which you have kept the laptop from this reflecting surface. You know the distance between the laptop and the mobile phone. And then you, at this fixed distance, you just have to vary the height of this mobile phone and see uh, if you can get an interference pattern, and you note down these heights that you are measuring, that you are keeping your mobile phone at, and then try to see the signal that is received at the laptop. So of course there one will be the direct path, the other will be the reflected path, and both these paths will interfere and give you an interference pattern as you move the height, as you change the height of this mobile phone. So you have to note down the points at which you get maximas and minimas, and this is a simple ray diagram, and you can actually use simple geometry to calculate what should be the path length, path differences given these quantities. You can actually find out the path difference in terms of the known quantities, and, and verify that with your observation. So this is the rough idea of the experiment. Again, for reflecting surface, you can put an aluminum foil here down, and you can keep your laptop on a chair, and of course you need a measuring tape to measure the height of the mobile phone. You can vary the height yourself and see the difference in power on the laptop. So on the left hand side, this is the schematic diagram of an observatory where you had a receiving antenna on a cliff, there is a sea surface in front of this setup, and the source is in the sky at a very far away distance. So there will be two rays again here. One is the direct path, one is the path reflected from the sea surface. And then as the source moves in the sky, you see these maximas and minimas, basically the interference pattern caused by these two rays. And uh, this was a very early setup used to do interferometry experiments. And here is on the right hand side, you see we have created similar setup. Uh, I have kept it on my bed. It is not recommended to keep it on bed because the mattress is compressible and your distance and length measurements might be affected by that. So I have kept this laptop on two boxes, and there is an aluminum foil beneath it, and I varied the distance of my mobile phone from this other end of the aluminum foil vertically. Uh, One more thing to keep in mind is that keeping your laptop in this orientation is not recommended. You either keep your screen facing the other side because the ray might hit the screen and then interact with the antenna, so you might get third ray coming from reflected from the screen. So to avoid that complication, you can just turn your laptop sideways.
You know where the receptor antenna is in the laptop generally?
Yeah, it is
In
mentioned.
the laptop screen, around the screen.
Okay, so I think Ashish, what we had discussed was to turn the keypad away.
Exactly.
Okay,
Yes.
so the reflection from that is the one that coming in the way of the reflected ray was the issue.
Right. So
Not the surface of the screen.
right. Also, not all laptops will have this antenna in the screen. Most of them, what I saw was the antenna was behind underneath the keyboard. So some laptops might have metallic covering behind the screens, and that might cause a problem. But yeah, in both the cases, you can turn the laptop around so the screen is facing the other way to avoid these effects of uh, like interactions of these surfaces of the laptop itself.
And also they can have the convenience of looking at the screen, right, without interfering with the experiment.
Right. Yeah. So this is the rough setup. Also, again, I will mention that it is not recommended to do this on a bed, uh, but if you don't have an option, you can try it. And also, this height, you can try varying the height of the laptop above this surface and see the difference in this pattern. Uh, you can try putting it on a chair or a small stool. It is also recommended not to keep this height too large, otherwise the reflected ray might have to travel much longer distance and it might not give you the best result. But those are parts of experimenting, and you can try different heights above this reflecting surface. Uh, and of course, you can try to figure out what is the expected uh, part difference between these two rays just from the geometry and verify that with your observations.
Yeah,
So,
much like the way you saw in the original cliff top
right.
interferometer, you will find that the easy calculation is made. A because of the direct ray and the one before reflection are parallel to each other. Okay,
Yes.
which is the case for very distant source, and that's not true in our case, as you will see. The second is you can imagine the receiving antenna or the radiating antenna. Okay, in this particular case, with reflection about the mirror. If you could go to that, yeah, right. So this will make your life easy in terms of calculation. imagine that this mobile phone has an image downward here, right? Exactly same distance h below the surface, and that would basically give you a easy geometry to work with for finding the path differences. After, of course, accounting for this extra pi phase shift due to the reflection. Okay, so you could take where the cursor is for I think Ashish's cursor is, yeah. If you go down similar distance, Ashish, yeah.
Yes, here in this direction.
If you go similar distance down, okay, yeah, somewhere there, if you keep it. So the ray will go from there to the laptop, okay, which will be exactly the same direction. Okay? And there is, so R1 and R2, R3 combination can be thought of as a single ray coming from the image of the green circle.
Yeah.
This might make your calculations easy, except don't forget to account for this extra pi. If you don't, then all that will happen is your minima will become maxima and maxima will become minima in your calculation versus the actual observation. So this is, and then you can work out the path differences and see how the height changes that.
Yeah, so that point is illustrated in this image on the left hand side, where you have the image of this receiving antenna, and then that becomes the baseline, and that determines the uh, interference fringe width basically. Yeah, so any questions related to this experiment?
So here, if water is placed instead on the ground instead of aluminum foil, will work or not?
Yeah, you can do that.
Like here,
Except just be careful about what frequency you are operating at and how much absorption water has. It may not be a good reflector at all those frequencies, so just be careful about that. At what frequency was the sea surface interferometer done?
It was a very low frequency, I guess close to 300 megahertz or so.
Right, at which water is a good reflector. In fact, it also depends on how pure the water is. Okay, distilled water has very different characteristics than one with salt and so on. So sea surface has a very special additional connotation about the salt content.
So can this method be used to see the contents of the base material also? Like this?
Probably. So what you will see is the depth of this modulation. Okay. For example, a clean cancellation would occur if the signals were of the same strength, right? Only then the cancellation can occur. Correct? You can arrange for the phase shift, but you cannot arrange for the amplitudes to be same, right? And they would, in this particular case, differ. In our case, they might differ significantly because we are the R1, R2 plus R3 might differ very much, okay, in terms of their squares, and that itself will change the level of intensity, even if things were perfectly reflected. There is also another issue which I am not getting into about the near field nature of the reflecting patch. Okay, it's very important, and this was one of the major considerations of the way if for example this receiving antenna had a directivity which could receive only the direct ray and not the reflected ray, right? You would not be able to see the interference that one saw, correct?
Yes.
This would happen if the reflected ray, the reflected patch was well beyond the transition zone between near field and far field, correct? Now this works because the receiving antenna is big enough and the patch that is responsible for reflection is in the near field of the receiving antenna. This would not work if the receiving antenna was small enough, okay, and had some directivity. Of course, they are mutually exclusive in the sense if it was small, it will look at broader angular range, and so on and so forth. But the important part is that the reflected ray and the direct ray should have a way to be received with equal or reasonable respect by the receiving antenna, okay, in terms of its directional response. This is if the reflecting surface were to be in the far field.
Sir?
So
Yes.
Yeah, sir, how the absorption coefficient of aluminium compensates the power we will be recording and noting down?
That will also play an important role, okay, but I think it's supposed to reflect pretty well, aluminum foil at least.
Yeah, yes.
I mean, it does have some, the finiteness of its conductivity or finite resistance will have effect, okay. But I think it will be minute, maybe beyond your detectable limits.
Okay, sir, so all this means small variations and all we can left out from our calculations, right, sir?
Yes, because we, in terms of what, other reflections and so on?
Yes, sir, yes, sir.
Yeah, so there the simple argument that works is things that are reflected from distant reflectors, relatively speaking.
Yes.
They have traveled long distances. The reflections also, they may not be perfect, okay? They may not be what are called specular reflections, okay? Not like a mirror-like reflections.
Yes.
There might be also some scattering associated with it. Okay? That means reflected stuff might go in various other directions than just the single.
Yeah, different angles and all.
Yeah, dictated by one ray path.
Yes.
So even all this, the weakness of the other reflections is what we are presuming in the relative sense, okay, and that the dominant effect of interfering with the direct path signal is for this the situation that we are considering in different cases, and that's why one wanted to be roughly away from various other scatterers and so on. But even if they do exist, we can ignore these because you can argue on these two grounds that A, the distance traveled in the process is going to reduce the reflection amplitude, and you will also have imperfect reflections.
Yes, okay, fine. Thank you, sir.
So Desh, I just verified the sea surface interferometer operated between 40 and 400 megahertz.
Right.
Yeah, and no observations were made above 400 megahertz.
Right.
So would a polished floor work?
Yeah, depends on how reflecting it is. Okay, at optical wavelengths, it might be doing good job. You will see at longer wavelengths, what does it do?
So basically a tile floor, because the other issue is that to uh, because if we need a larger distance to get that much of a foil paper,
Yeah, right.
right? So if I use the floor, because the floor is like it's large tile floor and like it is reflecting optical wavelengths because like it is a reflecting floor. So if it's polished well enough, like would it work or would it cause more reflected rays to interfere with the experiment?
Well, they will not reach the way the other reflections will be going elsewhere, right?
Right.
In fact, the corollary of that is that if you do have only a small patch of foil, right, you can cleverly put it at the correct place based on the heights that you have chosen.
Right. Yeah, I did experiment with that. We have to calculate and we have to see where the
Yeah,
reflected.
but since it will be a pain, certain patches you need not cover at all. Okay,
All right.
isn't it? Because you're never going to have that situation for the height range that you might explore.
Yeah. Okay. Understandable. Thank you, sir.
Yeah. So, as Adish suggested just now, you then probably don't even need the entire aluminum foil if you can calculate at what point the ray will hit, depending on the height. So you can just use a small household metallic plate to see the reflection.
In
So
fact,
that
after keeping the edge, the two heights fixed, you can move the plate to see an enhancement or reduction.
Exactly. Yeah.
Except in some cases based on the geometry and the way it will add, you may not be placed favorably to always get a peak, or you might be on some pattern, some location on the interference pattern. So that's why I don't advise that as the tool to figure out where you should
Right.
the reflecting surface. That cannot be trial and error. You can work that out and put it there, and then take a measurement.
so the instruments, because interfering again and again, varying the height, we would also have to change the location of the foil.
Correct.
So it would be discrete measurements rather than continuous pattern.
Sir, while taking the height of the laptop and the mobile, should we consider the the wavelength of the signal that it is transmitting?
The high, yeah. While taking it, what you should take into consideration is for the range of heights that you will change through for one of them. You should see that the direct path and reflected path do develop enough phase difference to see enough set of constructive and destructive instances. Okay?
Okay, sir.
Yeah. In fact, if you
In
have
fact, you can work out the phase difference and see what, in one case, what is the phase difference in one extreme and the other extreme, and keep don't take modulo 2 pi, actually keep the phase difference or part difference in units of lambda, and then see that that will tell you the number of fringes you are expected to get.
right, you can compare 2.4 gigahertz and 5 gigahertz fringes.
So this is a poor man's sea surface interferometer simulation. That's mainly because, like the astronomical source, which will have direct ray and the other ray before reflection parallel to each other, we do not have that luxury here.
So, sir, after completing the experiment, if we plot a graph, means like intensity versus distance, so we can get a proper, say, if the experiments, if the readings we get it correct, we can get a proper maxima and minima graph, right?
Correct.
Yeah, sir. Means it is like the mentioned here in the PDF.
Yeah, you should be able to compare it with your theoretical calculation. Okay.
Yes, sir. Yes.
Expectation of the peaks and so on. Should be. Except while doing all these experiments, when you have a particular setup, do vary the orientations of the individual ends, either the mobile phone or laptop, to just make sure that it's not sensitive to a certain orientation. Or if it is, try to understand which way it should be for the situation you're going to use it, so that you're not cheated by the additional effect of polarization sensitivity.
Yeah, so shall I stop sharing now?
Yeah, are there any questions? These are very simple experiments. They illustrate some of the basic principles that we routinely use. And of course, the sea surface cliff top sea surface interferometer was one of the major breakthroughs in the way one did interferometry initially, using a single antenna, right? Without using a pair of antennas. And that has its very important role in the evolution of radio astronomy. Yeah, that should work. I think there was a comment from Ahmed. No, sure. There is no single ray. There is certain area, but you can also work out what what area will be playing prominent role. Okay, and that's decided by the receptor and how it's going to look at it. Ideally, it's full Fourier optics that I mentioned last time in response to some questions. So we are any approximations we try to do with specific ray paths and so on is going to show up in the additional effects that would bring. So it's a wavefront essentially, and it's not just one ray. So you need to cater to all that, but you will find that if you go and actually do the sum and see what it really corresponded to, right? You will find that it corresponded to the sort of discrete ray description more closely than some other ray which was also participating but not so prominent. So another way of saying it is the average behavior from an area where the reflection is taking place is well modeled by the central path. Only to a certain extent though.
So, Jamil, you want to add anything?
No, Ashish.
Okay. So, if there
Any
are
other comments from anyone else?
So maybe from now they can perform these 4 experimenters, like they can perform these experiments, and if they find any difficulty, we can discuss it
You
later.
can do them in any sequence
Yeah.
and combinations of it, as long as you get to visit all the aspects that have been highlighted. Should be fine.
So you can discuss among your group, and you can discuss result among your group. So that will be better. Even if you can discuss with other group, that also be good. So then you can come to a conclusion. So if there are no comments, then we can stop and they can perform their experiments. So we can keep this time for their experiments. Is that fine, Desh?
So is there any limitation to height, maximum height that can be taken to the transmitter?
So in the
Sorry,
last
can you
experiment
repeat
you're
that
asking?
last part?
Is there any maximum height till which your transmitter can be taken, like in this, like your near field consideration should be there as well?
Yeah, I'm still not. I think your voice is not clear. Either my volume is very high or voice is breaking. You were talking about some near field considerations, right? And the width of.
Yes.
Yeah.
No, height, sir. Is there a maximum height till which the object can be taken? Like, should be taken after which the calculation will get wrong?
With respect to last experiment you're asking?
Yeah, yeah. He's talking.
Yes, sir, last one, yes.
Yeah. So he's talking about heights. I'm still not getting his words correctly.
So-
does any one of you hear him properly that can translate for me?
Yes, so actually he is saying that is there any upper limit for the heights? After that, the readings will not be calculated. Cannot be calculated.
There is. I mean, from the geometry, you can find out what is the maximum height that you should take it to for the distance separation that you have taken and the height of the other location. That you will be able to work out what should be the maximum height. There is also another consideration that the reflected ray, if it has to travel very long distance compared to the direct path, you will find its intensity is going to be rather reduced. And it will not give you a very deep null or, the destructive interference will not be deep enough. You will find the depth of modulation or the fringes will not be very high.
So it will kind of act like an nth maxima or minima. If the height will be maximum, right? Sir?
Yeah, but it will be sitting on a pedestal, which will be largely just the sum of the two intensities.
Yes.
The direct path will be dominating, and the other one will do a small wiggle on it. Okay.
Yes.
Because it's not either enhancing or cancelling things effectively enough because of the reduced intensity. So that is another consideration, which will be probably more loose constrained than the basic geometrical consideration. Okay, that given the height and the distance, height of one of them and the distance, you might find there is the other reflector, whatever, receiver or radiator being at height beyond a certain limit doesn't fit in with the geometry.
Okay.
Okay, so thank you, sir.
Thank you, sir.
All right. So I need to quit because I have a talk to give at 4. to
maybe-
organize.
Yeah. Sure, Desh. I think the meeting is also over. So
Okay, great. Okay, wonderful. So I think are we meeting in the late evening or something?
Yeah, it depends on these people. So if they have any query and doubts, and if they're facing any problem, then we can meet.
Yeah, but is there a time identified? Did they have any feedback?
I guess no. And today even we have a talk in the foundation talk. So need to check
Right.
because we may not get this link for evening sessions.
Okay. Right.
my feeling is let it be today because let them try things out, then they'll have more.
Yeah, exactly. I think they might have more questions tomorrow when they have tried out something.
Yeah.
That's right. Okay.
Thank you, sir. Thank you very much.
Yeah, talk to you
Thanks a
people
lot.
tomorrow again.
Thank you.
Same time.
Okay. See you tomorrow morning.
Yeah, tomorrow morning at 10. Yeah, sure.
Yeah, sure.
Take care. Bye. Thanks.
Take care. Bye.
Bye.